IGST3 cross S3 cross S3 cross S1 QSC.
Okay. Thanks, Andrea. And yes, I would like to present this novel proposal for a quantum spectral curve model based on some ongoing work I've been doing with Andrea himself, Ruven Prasek, and Roberto Tateo. I should also mention that the local group at King's is also doing a similar thing, Kolja, Philip, Simon, and Ben. But you can ask about it later, maybe. So to be very brief, the quantum spectral curve is a method that's to compute the spectrum of planar AdS₃ correspondences. And it's basically a Q system, which is composed of two elements, the Q functions and the QQ relations. The Q functions are functions of one spectral parameter with some branch cuts, and that contain in their asymptotics the quantum numbers of the operators we wish to describe in the dual CFT. The QQ relations are functional relation between these Q functions, and their structure is determined by the global symmetry of the AdS₃ models you're interested in. These are the quantum spectral curves that are so far known, with the relative symmetry and the symmetry of the Q system. We see some very familiar faces, such as n = 4, ABJM, and also this AdS₃ cross S3 cross T4 model. But today, I would like to propose a quantum spectral curve for this other AdS₃ model, AdS₃ cross S3 cross S3 cross S1, with pure Ramon-Ramon fluxes. This model exhibits integrability if 16 supercharges are exactly conserved, and this imposes some constraint on the geometry. This constraint can get resolved if you introduce a parameter alpha, which is basically related to the ratio of the radii of the three spheres. And this free parameter is also contained in the symmetry group of this spacetime, which is two copies of the exceptional Lie algebra D2 alpha. Alpha is also contained between 0 and 1, by the way. So there is immediately an obstacle for a quantum spectral curve for this model, and this obstacle is that in the literature, the QQ relations are not known for this exceptional super Lie algebra D2 alpha. There is a way around it. You can consider a simpler model where alpha is equal to 1/2. This in the geometry means that the radii of the three spheres are the same. And in this case, this exceptional super Lie algebra reduces to the more simple orthosymplectic OSP 4/2. So the symmetry of this spacetime, when the radii of the three spheres are the same, is two copies of OSP 4/2, for which the QQ relations are already known in the literature, and they're also very similar to the ABJM Q system. So goal of this talk is to make a full quantum spectral curve proposal for this more symmetric case, but in the end, I will also briefly propose some QQ relation for the more exceptional case D2 alpha, which, as far as I know, are not known in the literature. So let's start to describe this Q system for OSP 4/2. We have two copies of them, but for now I'll only talk about one copy. We have 16 Q functions in it that can be grouped into these four families, P, Q, which are the most important ones, and these spinors and anti-spinors. The QQ relations for this Lie algebra can be derived from a simple set of correlations, which are these three matrix equations. The first two simply connect the P with the spinors and anti-spinors, while the last one lets you build these Q functions from the first three. This epsilon is just antisymmetric tensor. So in some sense, this Q is less fundamental than the others. You can determine it completely by all the other 12 P, Q, P, S, and S hat. Then we need two copies of this Q system, so we'll have a total of 32 Q functions. The one on the L wing will have the same notation I introduced right now. On the R wing, we'll just add a dot on top of the Q functions. Then, to fix the quantum spectral curve, we should impose some analytical structure on these Q functions. And the first thing you should do is to impose power-like asymptotics in both of these two wings. In particular, the P and P dot function will contain the SO4 labels of the operators in the dual CFT, so they will have integer asymptotics, basically. While the Q functions will have SL2 labels. So this will contain the anomalous dimension you're interested in computing in the end. And it will be, of course, non-integers. Finally, you have to impose some branch cut structure, and this is very similar to the other quantum spectral curve models. P and P dot will contain will have a single short branch cut on the real axis between -2h and 2h, where h is the Hooft coupling of the dual CFT. And Q and Q dot will have a long branch cut on the real axis between minus infinity and minus 2h, and between 2h and plus infinity. However, this very simple analytical structure already gives some tension, creates some tension. In fact, if you start from the p function with this short branch cut and use the Q relation, you can reconstruct the possible analytical structure of the Q functions. You get two different possibilities, one in which the Q's have a ladder of short branch cut in their upper half imaginary plane, and one in which they have a ladder of short branch cut in the lower imaginary plane. So how is this consistent with our assumption that the Q function have a long branch cut? Well, this is where gluing comes to the rescue. The idea is that you have these two possibilities, either this, where with a long branch cut, or these two guys where there are a ladder of short branch cuts. If you have the long branch cut structure, you should be able to start in the upper half plane, find no branch cuts, cross here, and get to the lower half plane where there are still no branch cuts. And, but if you have this other analytical structure, the only way you can reproduce this is if you impose that you start in the upper half plane with this Q down arrow, which has only branch cuts here, and when you cross the real axis, you end up with this other analytical structure. This condition, which is basically just what happens when you analytically continue to the real axis, is encapsulated in what we call gluing. And for this AdS₃ model, this gives also the opportunity to make these two different wings talk to each other. In particular, we should impose that if you start from this analytical structure and you cross this branch cut, you end up in the other wing and you find Q dot with this type of branch cuts, opportunely reshuffled by some constant matrices, G or G hat, which are called the gluing matrices. So once you impose this, all the tension in the Q system is resolved, and you've basically completed your proposal for the quantum spectral curve. Then it's time to do some testings, and the main test we have performed so far, but it's still some work in progress, is the asymptotic Bethe ansatz limit. To do this, you should take L to infinity, where L is the length of the operators in the dual CFT. And in this case, the quantum spectral curve equations simplify enormously, and you can actually solve them exactly. From this limit, some Bethe equations emerge, and they should reduce to the asymptotic Bethe ansatz equations, which are known in the literature from the S-matrix bootstrap. We checked that they're actually the same, at least in some cases. By doing this, we also get some prediction for the dressing phases of the S-matrix here, which are still not fixed. In particular, the structure we seem to find is the following. These dressing phases are composed by a BAS phase, which is the same as n equals 4 super Yang-Mills, a piece which we call sigma extra, which was already found in the other AdS₃ model and contains these famous logarithmic branch cuts, and a new piece. We do not have, unfortunately, yet an analytic expression for this sigma nu. We only know it's given in terms of a solution of a linear integral equation. But we also know it disappears for some very symmetric states, where in particular these spinors and anti-spinors Q functions are the same. Now, just in the last minute I'll briefly talk about an extension to the generic alpha case, and in particular I'll try to propose a Q system for this Lie algebra. Our ansatz is that the Q functions are the same as the OSP4/2K, so we still have these four families. However, what changes are the correlations. And as you see here, these alpha parameters enter the shifts that appear in these QQ relations. From this family of three equations, we can derive all the QQ relation and the Bethe ansatz equation, and the nice thing is that they actually reproduce what you should expect from a theoretical point of view. Furthermore, it's pretty easy to check that they reduce trivially to the OSP4/2Ks at alpha equals 1/2. Of course, there's still some open problems we need to address before finishing. The first thing we should do is to compute an analytic expression for this novel dressing phase sigma nu and check that it satisfies all the assumptions of a dressing phase, like unitarity and crossing. We should also extend our ABA limit, because what we did so far is only include the so-called massive modes, but this model also presents of massless modes, which we should try to include in the ABA limit. And finally, we should also try to do some numerical computation for this model to actually compute some spectrum. Unfortunately, this is probably harder than n equals 4 super Yang-Mills or ABJM theory due to the presence of logarithmic branch cuts, but I think tomorrow we'll hear something more about this for the other T4 model. And finally, we should also try to extend our construction to the full D to 1 alpha case, because so far we only have Q correlation and some basic analytical structure, but no gluing or other steps. Thank you for your attention.
Questions?
How do you include alpha, not 1/2? You mentioned this, but you didn't.
Yes. So basically, you choose alpha. Which there is alpha, and 1 minus alpha. And then the idea is that you still.
Can you use the microphone?
Sorry. The idea is that you should still assume the same analytical structure for the P function, and then using this Q correlation, you get this strange analytical structure for the Q functions. Where now the ladder of branch cuts is not evenly spaced, but the spacing depends by these alpha and alpha hat parameters. Another strange feature, it seems to me, that if you take alpha equal 1/2, this alpha hat is also equal to 1/2, so these two branch cuts will collapse on each other somehow. So there seems to be some non-trivial splitting of branch cut if you take generic alpha.
So does things simplify if you go to the alpha equals 0 limit, or alpha equal to 0 or alpha equal to 1? Do you get any sort of simplification, or?
Well, there should be some connection with the other AdS₃ model, because in this case, D to 1 alpha becomes PSU 2/2. But I don't think it's so trivial to see, because in that case, some of the connection in the Dinkin diagram actually break down. So I'm not sure what happens. It seems to be some sort of singular limit, actually, of this D to 1 alpha. While this alpha equals 1/2 is completely regular, even from the Lie algebra point of view. We should investigate.
There's a question from Volodya.
No, not really. Even in the literature, I don't think it's known. But also from the, yeah? Okay, thanks. Maybe we should investigate.
So how about the S matrix for the generic alpha?
Yes, so these papers I've cited here actually do the generic alpha case, but the dressing phase, it's not fixed. There's only a crossing equation written for it, but it's not solved.
So what's the dimension of this R matrix?
What, sorry?
S matrix dimension, local.
Well, it should be, but again, there's only a crossing equation in the literature. There's no explicit form, as far as I know.
Mm.
Other questions? That's one in the corner by David.
What about this new piece you find is a complicated equation and not related with the previous version?
Yes, so at the moment we just have it in terms of a solution of some unknown nonlinear integral equation, which depends on the state you're describing. We don't know, since we don't have an analytic solution for this, we don't even know if it's unitary or it satisfies some crossing equation. To do it, we should solve it and find an analytic expression for it, but still work in progress, let's say.
A question there.
So what does it mean that the phase is BS times extra times nu? I mean, you could have said it's nu. Are you just taking out the branch cuts? I mean, why do you say the phase if there's an unknown piece is BS times extra times nu? I mean, you could have said it's nu. You're taking out the branch cuts, so what do you do with it?
Sorry, I didn't understand the question. Ah, right, of course. But, well,
what's the logic? I mean,
if you take these special states, it's not really new. These two parts are already inside this other AdS₃ model. So it's not really new. The only new piece is this one, sigma nu. The rest you find already in some other models, which should be related to this in some sense because, well, they're connected by some compactification, basically, on the string theory side. But yeah, I agree. The full object is new, like the full phase is new.
Yeah, okay, it's time to change to the next talk. So let's thank Nicolo again.
Wait, don't start me yet.
No, I won't start the clock yet. Okay. And next we have Julius, who will tell us how to go from Glueballs to massive strings.
Thanks very much. Thanks to the organizers for giving me this opportunity. Today I'll tell you about work done over the past 2 to 3 years, mainly with Nika, who's at King's. All right, so let me start. I like to start talks with this question, which is, what does it mean to solve a quantum field theory? I mean, I know this audience doesn't need motivation, but just in case. Right, so in order to solve a quantum field theory, you need to know all correlation functions. In general, this is quite hard, but if you have a conformal field theory, then it becomes slightly easier because you just need to solve all 2 and 3 point functions. These 2 and 3 point functions together are called the CFT data of a conformal field theory. The 2 point functions are called the spectrum. 3 point functions are characterized by numbers called structure constants or OPE coefficients. So then the next question you can ask is, suppose there is some quantum field theory whose spectrum I know. Can I take the knowledge of the spectrum, add into it constraints from crossing symmetry and some constraints from holography, and use this to extract OPE coefficients? That's the question I like to ask in my research, and I want to tell you a bit more about some progress that we've made in this direction. Right. Okay, so again, this slide is probably not needed for this audience, but n equals 4 super Yang-Mills is the theory that we're going to look at. In particular, we consider the planar limit, where we take the Yang-Mills coupling to 0, the number of colors to infinity, in such a way that the 't Hooft coupling is kept fixed. The reason we consider this limit is because the integrability of the theory, this theory becomes integrable in this limit, and also the only states that we need to consider are single trace states. Single trace states are just traces of L objects, and these L objects are made up of your favorite number of covariant derivatives acting on your favorite combinations of fields in the n equals 4 Lagrangian. Operators in the theory are labeled, therefore, by the bosonic symmetries they have. The bosonic symmetries of n equals 4 super Yang-Mills is the 4D conformal group times 6 SO6 R symmetry group. So in general, you have 6 unique labels that define a single trace state. These 3 labels refer to the SO6 R charges, and these 3 labels label your 4-dimensional conformal group. Representation, the representation under the conformal group. And out of these 6 labels, 5 are integers or half integers, and the dimension in general could be a non-trivial function of the 't Hooft coupling, of the parameter of the theory. And in general, if you want to solve the spectral problem of this theory, you want to understand the dimension for any value of the 't Hooft coupling. What you can then do so the dimension is what we want to study, and we want to study operators or single trace states in this theory in the limit of large 't Hooft coupling. So in the limit of large or strong 't Hooft coupling, the operators in this theory can be characterized in the following way. So instead of measuring the dimension of an operator, you can measure the eigenvalue of its quadratic Casimir. It contains other things, but also contains spectral information. And this object, you can expand its strong coupling, and it will have an expansion like this. It has some expansion in powers of 1 over square root of lambda, with the first coefficient in front a number which I like to call delta, which corresponds to the string mass level. And this is because single trace states at strong coupling are dual to massive strings. So that's how you can actually see this relation. The planar spectrum of the theory is solved. A long journey which was pioneered by various members of this community, and well, my favorite way of doing it at least is called the quantum spectral curve, and here's the spectrum of the theory. So, right, so 2 years ago with our collaborators, we got these plots. And I have 5 minutes left, okay. And you can look at these plots and you can see that we have all states in n equals 4 super Yang-Mills below some bare dimension. That's not the focus of this talk. The focus of this talk is to look at what happens to these states as you go towards strong coupling. As you go towards strong coupling, you can already see that the states band according to the string mass level in the following way. So there's an overall envelope with 2 times square root of some mass level times lambda to the 1/4. That's the first thing to observe. The second thing to observe is that the spectrum itself organizes into Kaluza-Klein towers. And the reason that happens is because as you're going to strong coupling, in a holographic picture, you're probing the flat space limit, so you expect the formation of these towers, and we see both of these things. So now that we have the spectrum, the next thing to ask is how do I extract OP coefficients from this? So just before we do that, let me give you a bit more paperwork about the spectrum at strong coupling. Yeah, that's fine, thank you. Paperwork about the spectral data at strong coupling. So as I said, we are probing the flat space limit. Massive strings organize themselves into Regge trajectories. They look like this. So you can do a Regge trajectory delta string mass level versus spin. And basically, at each value of delta and L, there will be some operators that you exchange, some massive strings. Most of the research in this community has been focused on the leading Regge trajectory, and that's because the leading Regge trajectory is non-degenerate. So whatever Maria was telling you about, whatever Benjamin was telling you about, Alessandro, all of this is on the leading trajectory. I like the subleading trajectories. The reason I like them is because for a given vertex here, for a given value of delta and L, you have not necessarily a single operator. And the question that Nika and I tried to ask is spectral information plus constraints enough to extract real information about these? Turns out the answer is yes, and in order to see that, we have to play a game which starts by the work of various people at Oxford over the past few years. So as we heard in the morning, these various people, what they've been doing is computing some string amplitudes in the flat space limit of AdS and systematically computing curvature corrections to it. The point, from our point of view, is that every time they compute a curvature correction, they get some constraints on OP data. So you can focus on some OP coefficients, expand them in a nice way in terms of some numbers here. And essentially, every time Fernando and friends solve a new order, solve the next curvature correction away from flat space, they get some constraints on these Fs and Js. Js, as I showed you in the first slide, characterize the dimension. Fs characterize OP coefficient. Okay, so that's the setup. And now I'll show you some results and stop once I've shown you the results. Right, so the first thing we did was we considered 4-point functions like this, where you have 2 gravitons and 2 KK modes. In that case, again, we studied states in the subleading trajectories, and we saw that there is actually quite high degeneracy. So this point has degeneracy 3, this point has degeneracy 7, this point has degeneracy 13. And what we wanted to do was input spectral data into constraints that you get for CFT data of these states and try to extract OP coefficients. So we did that. For all 3 cases that I described. I'll spare you the technical details, but the surprising thing is that we found that in all 3 cases, it seems that a majority of the OP coefficients seem to vanish at leading order, meaning most of the OP coefficients seem to be subleading to a minority of OP coefficients at strong coupling. So this was something very intriguing that Nika and I noticed 2 years ago, and then we tried to explore it a bit further. And we tried to explore it further by doing this. We said, okay, fine, let's not do Kaluza-Klein towers, let's instead study really the subleading Regge trajectories. Yeah, one sec. I have 1.5 minutes, that's great. So then we tried to play in the same game. We took constraints that Fernando and friends graciously computed for us. And we computed spectral data on our own. We made some assumptions based on, well, inspired by work done by Arkady and collaborators. And essentially, we tried to see if we can solve this system and unmix these OP coefficients on subleading Regge trajectories. We also had another piece of input. The other piece of input, again, I will spare you the technical details, but essentially, the other piece of input comes from the fact that if you actually stare at the subleading Regge trajectories, you will see that some Regge trajectories vanish at some point. But then you can always ask the question, what if I continue the Regge trajectories below the point that they vanish? And this gives you some more constraints on OP data. You can also construct what Andrea and friends call Regge bridges, which are an ingenious way of taking the subleading Regge trajectory onto the leading Regge trajectory and impose further constraints. Anyway, we do all of this, we fix a lot of parameters, and this is the result. It's, again, there's not really too much that you have to see here. The important caveat that I have to give you is that there are a lot of free parameters. We start with many free parameters, we end up with fewer free parameters. We fix them using slightly ad hoc assumptions. We get a result which has unsatisfactory from an integrability point of view matching to numerical data, but does have some matching. But the point, if you believe all of this, with all of this caveat, you will see that we see this vanishing of OP coefficients again. So it turns out, if you believe us and our assumptions, again, we are able to show that an infinite number of OP coefficients vanish on the subleading trajectories as well. So that's something interesting. And yeah, so I'll finish now with basically, my conclusion is the following, that yeah, it seems like there is some emergent symmetry selection rule at strong coupling. We've produced some evidence for it. We're in the process of producing more evidence. As Shai said, probably one should study in other theories as well. So we're trying to look at it in ABJM, maybe try to do string computations, etc., etc. So yeah, or also maybe we can use this technique as well. So yeah, that brings me to the end of what I wanted to say scientifically. The last thing I'd like to say is that roughly 20 years ago, this community started by a paper by Minan and Zarembo, and then yesterday I took this picture. So we're still at it 22 years later, and so yeah, so I hope, I wish everyone the best in the research. Thank you.
So I would like to ask, what would happen if you continue the spin to even lower, like lower than -2?
Yeah, we tried to do that, but our numerics was not, we were not careful enough with it. So I don't know the answer yet. I mean, we tried to do it, but we weren't very careful, and then we abandoned that. So, but it's something we need to explore. So.
Thanks.
Other question? By Benjamin.
I think I already asked you this question once, but I don't know if you made progress on it. So I was wondering if the zeros that you are finding could be explained directly by some computation in flat space string theory.
Yeah, that's the hope. We haven't made progress there. But you're right. In theory, one should just be able to construct the vertex operators directly and then see. And this is something that we should do, but we haven't done yet. It's something that we have in mind, but we haven't got down to doing that yet.
So what's the status in ABJM at the moment?
Well, okay, I mean, the status in ABJM is, again, it was hinted at by Shai. There are these Z parity odd operators. which one needs to try to understand, right? And if you want to play the same game in ABJM, then you can't, there's not just one type of long multiplet, there are up to 3, depending on whether you have even or odd spin. So yeah, right now, I think the status in ABJM is just to try to see if we can find these parity odd operators. We have some ideas about what they could be, but nothing concrete to say. But ideally, if we find that, if we find like a satisfactory way, I mean, if we find some operators which then at strong coupling match the predictions that they have, for example, then one could play this game.
So one needs this input from integrability to...
Yeah, I mean, so there are 2 things to do in ABJM. One is just to find the operators that they predict that exist. And then once you've found them, then you can go to subleading in ABJM and try to play this game, which I spoke about today. So there are 2 things. We're still trying to do the first thing. So yeah, we don't have anything concrete there yet, but that's something we're thinking about.
Okay, if there are no other questions, let's thank Julius again. Chiara Paletta, who will tell us how to detect algebraic integrability of the deformed Rule 54 model. Please.
So let me start by thanking the organizers for giving me the opportunity to present my work. Today I will discuss some ongoing work with Thomas Prosen in the University of Ljubljana. And the talk will be about the detection of algebraic integrability of deformed Rule 54 model. Since maybe those models are not familiar for the majority of you, let me start by introducing what are these rules. So imagine that you want to describe the dynamical evolution of some system, and you want to really find what is the possible simplest deterministic dynamic that you can think of. So let's look at this picture. In this picture, the time is going downwards, and this system is discrete in both space and time. This is the definition. The definition of a cellular automata is a system for which the evolution of one state only depends on the nearby cell of your system. Now, for this type of simple model, each cell can have 2 values, 0 or 1 or black and white. Now, we are interested in the evolution of this particular cell, and this one is in one state, and the dynamic given by this Rule 54 is the following. If at least one of the 2 states here is in the state black, then the cell that you are looking at will change state. So for example, let's look at this. We are starting from white, at least one of the 2 is black, so white will go into black. And you can look at all the others, so 2 white, the state does not change. If you have 1 black, it changes, and if you have 2 black, it also changes. There is a nice review of this model is given here. Now, this is really the simplest model you can think of, but surprisingly enough, a few years back, it was proven by Thomas Gombor, who is also in the audience, and Balázs Pozsgai, that this model is integrable, and furthermore is Yang-Baxter integrable. Now let me describe the dynamic of this model, and then I will move to the deformation that me and Thomas are looking at. So this model, the dynamic is given by one operator that is acting on even and odd side, so is periodic every 2 steps. And the rule that I was given, you can really imagine them as element in one matrix. Those are some transition rule. So let's take this model and let's add some deformation on top of them. In particular, Thomas introduced this deformation in 2021. He took the first state, so before in the undeformed model, if you have 2 white close, then nothing white goes into white. But now let's imagine that white can go into white or it can go into black with different probabilities alpha or beta. And also in this model, in this other rule, you have 2 white, let's say that the black goes into black with transition gamma, or it can go into white with the rate delta. Then what he did was to naively count the conserved charges, and he observed that conserved charges were scaling linearly with the length of the system. And furthermore, he also used some numerical technique. For instance, he was looking at spectral level distribution, and he observed that even the quantum deformation shows some sign of integrability. So since I started in Ljubljana, what we try to do is to prove that this model is integrable, and even more, it's Yang-Baxter integrable. So this model is really like the simplest model you can think of. You start to add some quantum deformation, and surprisingly enough, you find that is integrable, but is Yang-Baxter integrable. So to show this, I will move into the technical part now, just to tell you that it's not very easy to detect algebraic integrability. So if someone would have come to me and show this model and put a bet, like, would you guess that this model is Yang-Baxter integrable, I will probably have bet no. But after some work, then we managed to show that Yang-Baxter integrability is also there. So my take-home message is that Yang-Baxter integrability is not as rare as we used to think. So let me now try to move into the proof. Okay. So one possible way that one can check integrability is the following. This matrix U is the matrix that has a matrix element given by this square that I was showing before. So one possible way is to check integrability is, can I identify this U operator as the Lax operator that is identifying my Yang-Baxter model? Now, to do that, there is a formalism that has been developed in these papers, where we all know that the definition of integrability is via this RLL relation, but we can also take one space and double it. So one way to detect integrability is to ask if you can associate the U, your dynamical evolution, with the Lax of the integrable model. But unfortunately for this model, this simple thing didn't work. But then we were thinking, is there still some hope that the model is Yang-Baxter integrable? And luckily there is. So to prove this, we really needed to use a different strategy. And the strategy was to notice that if you take the dynamical evolution of your system and you check which is the charge, the first non-trivial charge that commute with it, you will see that the first non-trivial charge has interaction range 6. And then now this range 6 charge is really the main protagonist of our proof, because what we did was to use the boost automorphism mechanism to show that this charge Q6 belongs to a tower of conserved charge of an integrable model. So the question on integrability can be brought into a different form, that is, does Q6 belong to a tower of conserved charges of an integrable model? And so this part is really, really technical, but you can think about this boost operator as really an operator that you apply to one of your charge and you construct the next conserved charge. And what happens for this model is that if you start from Q6, you can get the next charge commuting with it using the boost that has interaction range 10, and both of them now commute. And this is now a strong indication that the model is Yang-Baxter integrable. I want to be precise, like this is not really a proof, but it comes from an old conjecture that is called the star triangle hypothesis. It says that a sufficient condition for a model to be Yang-Baxter integrable is that the first two non-trivial charge commute and the second one is constructed from the boost operator. What we also did was to apply the boost again, and we got also the next conserved charge. I want to emphasize that now this is a charge acting on 14 sites, so if we didn't have the algebraic structure, then to get this charge you really would need to use a very powerful cluster. But then we got this charge, which we checked commutation, and then we also checked that it commute with the dynamical evolution. And then we used this charge to construct the Lax operator perturbatively up to order U cube. Now this is a strong indication that also this model is Yang-Baxter integrable, but to have a complete proof of this, we would need to compute many more conserved charges and then resum. This was a method which was developed by, you can find information in this paper, it's called the Lifting Integrable Models by Anna and Marius, which are also in the audience. Unfortunately for this model, this method does not really work because all the matrices that we are dealing with have these dimensions, so it starts to become very, very complicated. So let me emphasize that even if this model is very simple, Yang-Baxter integrability also appears here. Let me conclude. I was giving you a very strong perturbative evidence that a deformation of Rule 54 model is Yang-Baxter integrable. And something else that we are doing with Thomas is to take this model, so the deformation I showed is quantum, but you can also restrict it and make it stochastic, and we put some open boundary condition and we obtain an analytical expression for the NS. But again, the model is simple, but the expression of the NS in terms of matrix product operator involves metrics which have infinite dimensions. There are many other open questions. First of all will be to really prove that the model is integrable, so finding the full Lax operator. But then there are many things that we don't understand. For example, why the first non-trivial conserved charge has interaction range 6? Is there a way to understand this, not by brutally compute, but from just the expression of U? And then in this model, the transfer matrix that you can build, it commute with U, but somehow it does not generate U itself. So why is this happening? And then this is some discussion we are having if what happens in the open boundary condition in terms of the Scalianin algebra. And with this, I thank you for the attention.
Okay, maybe I wasn't paying enough attention, but why is it called Rule 54?
Thanks, yeah, for the question. Maybe, yeah, I didn't say it, so it's good to. So it's called the Rule 54 because if you look at this, so the first three are the same for all these possible rules. But then what changes is the output state. So if you start by reading from here, this is white. So 0, 1, 1, 0, 1, 1, 0, 0. You can take this number, this is in basis 2, but if you go to base 10, then you get Rule 54. Yeah. Thank you.
Hi. So is there a way to detect kind of integrability experimentally by just modeling and checking some, I don't know, chaos, non-chaos?
Yeah, so I think Thomas got interested in this model especially for this, because if you compute level spacing distribution, he found Poisson statistics, so the model shows sign of empirically check of integrability.
Hi. So did people study also quantum deformation of other cellular automata models or not really?
Sorry, you are asking if
people study the quantum deformation of also other cellular automata models?
Yeah, so there is a letter, there is a project by Thomas where he was introducing this model and also the formation of another model. I don't want to say wrong because I cannot really remember if it was 201. So it was the same. Instead of F00, he was putting this 2x2 matrix. And then you can try to ask the same question if it's still integrable or not. But other than that, I'm not sure how much is done in terms of deformation. yeah, it's something that we are thinking about, but we didn't really go there in finding the most general, for example, deformation you can add. Yeah. Thank you.
I have a question. Is this a unitary process? That means, is it reversible in time or not?
Yeah, so Rule 54 by itself, it's reversible. Then the quantum deformation, you can make it unitary or stochastic because this is the matrix that is now governing your dynamic. So you can say, you can make this F00 unitary, and then all the dynamic will be unitary, or you want to focus on stochastic deformation, so you can impose that these two sum to one. It's really very general. These four parameters are can be complex, can be anything.
I thought maybe it is related to what the model, series of the models which are called directed percolation or something like that, no? Looks like a percolation.
Yeah, maybe, yeah, but I'm not fully sure. I mean, yeah, this name sounds familiar, but I cannot really say if it's related. Maybe it is related, but yeah, thank you.
Thank you.
So one last question.
So thanks for a nice talk. Do you have any hints of what could be the R matrix, even like perturbatively, if you know the Lux operator, or?
Yeah, so the problem is that now this Lux operator, it is acting on two legs. The first one is acting on two Hilbert space, so like 4 to the square, and the other one is like just 4 by 4. But then if you go into the RLL, the R matrix is acting on two spaces, and both of them are squared. So it will be a matrix of 4 to the 4th. Now, you can try like to take this equation and write it perturbatively, and you probably will get this R. So if you fix V equal to 0, there is a conjecture in the paper by Thomas and Balash that the R factorizes as product of two Lux operator. And from here it also follows trivially that if you put V to 0, then you will get just identity. But higher order, I'm not really sure. We didn't try.
And you also don't know if it's difference form or not?
Probably it will be non-difference form for the way these medium range model are constructed. Yeah.
Thanks.
Another way that we have also attempted, but we didn't go very far, is to try to solve the Sutherland equation. Because you can take Yang-Baxter equation, take the first derivative, and you will get the Sutherland. And then you can use the fact that the first derivative of the Lux is, and if you put U to 0, it will be the charge Q6 that you have. So you use Q6 as input and get the R, but then it's hard because it involves R and also the first derivative of R. So yeah.
Thanks.
Thank you. If anyone has any clue on how to show the full integrability, I will be very, very happy to hear.
Thanks. Let's thank Chiara again. Our next speaker is Tim Meyer, who will tell us about integrability in angular dipole deformed n equals 4.
Right, thanks for the chance to speak about this project that I had together with Stein van Tongeren. And there's actually a paper that should appear in the next days about that. So this topic is, well, it starts from this AdS₃ correspondence, especially in the case where it relates the AdS₃ string to n equals 4. So both of these models, they share the same kind of symmetries, and they are both integrable, which especially on this on the field theory side means that we have some control of the 2-point functions via some integrable spin chain picture. As Sibylle was already mentioning in her talk, people got attracted by a kind of integrable deformations, especially these so-called homogeneous Yang-Baxter deformations as deformations of the string theory side. So this leads to some deformed class of these models, which are now symmetric under some kind of twisted symmetry. And there's a conjecture that if you apply the same kind of twisting to the field theory side, that you get a deformed theory here that should correspond to these homogeneous Young-Baxter deformations. Right. So in this talk, I will now tell you a little bit for this particular example of this angular dipole twist, how to get this deformed theory, and then I will shed some lights on this question marks here on observables, especially the two-point function, and how to find spin chain integrability in there. Okay, so how do we actually deform this theory? This we do by deforming the product between fields. So first we formalize this pointwise, so this normal pointwise product between fields by introducing this map mu, which is just a fancy way to rewrite this pointwise product. It's now acting on this tensor product of two functions, and we can then introduce an object that is called a Drinfeld twist, which then defines a new twisted product on fields. And it's just the composition of this pointwise product mu and this inverse twist function. Okay, this twisted product is then what we call a star product, and we simply just write f star g. It turns out that this is non-commutative, but it remains associative. Well, and the idea of this deformation is then to replace every product in the undeformed theory just by all these star products in principle. To give you some examples, one relatively famous example is such a twist here, which leads to the so-called beta deformation. So this twist is basically just built from this exponential of internal R charges. So the star product then just introduces some phase factors in front of the product of two fields, depending on the charges measured by these Qs here. We can also replace these Qs by space-time symmetry generators, for example, translation generators, and then this star product introduces a non-commutativity between coordinates. So this would lead to true non-commutative field theories in the end. The twist that I would like to present now is something in between. So it's built from an internal R symmetry charge Q and a rotation generator in the 2-3 plane of space-time. And this is then what we call the angular dipole deformation. The star product then basically shifts the angular argument in this 2-3 plane of the individual fields by something that is proportional to the charge measured by Q of the opposite field. Okay, so if these fields are now, like in n=4, fields in some adjoint representation of a gauge group, from this expression it's already clear that this quantity here is not a nice object under normal gauge transformations. But we just follow the guiding principle and replace product by star products, considering star gauge symmetry instead. So an adjoint scalar field now, for example, transforms with the star commutator instead the normal commutator. Similarly, we can define a gauge 1 form that now transforms as such, and this also defines an exterior covariant derivative. Okay, having that, we can then write down a deformed action for Young-Mills, for super Young-Mills. This is how it looks like, and also here in principle, products are just replaced by star products. So this is now the deformed action. It's gauge invariant, and we can start doing field theory computations with it. So for example, we could try to look at two-point functions of gauge invariant operators. But for this, we first have to define gauge invariant operators, because the usual construction with single trace operators is not gauge invariant anymore. So in principle, we can take the trace of such a star product sequence of fields, but it's just not gauge invariant because this star commutator here, so the star product shifts the argument of this gauge transformations that appears here, but in different ways, depending whether it appears after or in front of the star product sequence. So those things, they don't cancel against each other. What we can do to cure this is to introduce a Wilson line that now goes on a circular path in the 2-3 plane, which only has the task to cure, in principle, this difference here and bring those positions back to the same, so that these things can cancel. But this means that in every kind of gauge invariant operator, we now have to include these Wilson lines. Okay, but these are then the operators we want to compute two-point functions of, and in which we now want to find some kind of twisted spin chain picture in the end. Okay, as you might be familiar with, in pure n equals 4, you have the spin chain picture, which has cyclic spin chains. So we would like to see whether we also have some what's happening when we move fields around this trace here in these operators. And in fact, we can move one of these fields, for example, from the front to the end, so this phi 1, but then the star product is now acting in the opposite direction, and we have to account for this change by introducing such a boundary twist here. Here, this capital lambda is in principle proportional to the R charge measured of all these fields together, and lambda 1 is just measuring the R charge of the field that is moved, in this case phi 1. Similarly, these M23s here, they act as Lie derivatives on the appropriate fields as well. I said they act as Lie derivatives, which means they have in principle two parts. One acts as a partial derivative with respect to the angle in the 2-3 plane, and the other measures in principle the physical spin of the particles. So we would like to translate now these things to spin chain language. This immediately works for this spin measuring part. This has a clear, definite meaning in terms of spin chain language, but these partial derivatives, they don't have such a meaning immediately. And similarly, also these Wilson lines, they just don't appear in the spin chain picture of n equals 4. So what we do is to restrict the space-time dependence of our operators to be just in the 0-1 plane. If we do that, then these Wilson lines, which go on circular paths in the 2-3 plane, they shrink to a point and become trivial. And similarly, also these partial derivatives here, they trivialize. So this is the only thing that is left over from these boundary conditions. And now all these things, they have a definite meaning in terms of the spin chain. So we can then write down the planar one-loop Feynman diagrams that appear in the two-point function of these operators, and it turns out that they arrange themselves in the same kind of sums of nearest neighbor interaction that we find in the undeformed n equals 4 as well. So we can actually reuse the same kind of spin chain picture that we have in the undeformed case, where we just have the same nearest neighbor spin chain Hamiltonians. But now these gauge invariant operators that we have, they are now corresponding to some kind of cut open spin chains, where whenever we move a spin over this cut, we have to account for this change by imposing twisted boundary conditions. The anomalous dimensions of these, the planar anomalous dimension at one loop of these operators then can be shown to, or this is actually what we did, then correspond to the spectrum of this Hamiltonian, which, like in the undeformed case, is the sum of all these nearest neighbor Hamiltonian. But again, we have to account for this twisted boundary condition for this one interaction that acts over this slit here, this cut. So such twists, they are also known in the literature, and they are shown to be integrable, and they can be solved using Bethe ansatz and Bethe equation. So that means that in this two-point function of our gauge invariant operators, we really found some kind of deformed or twisted spin chain integrability in this picture. So, right, in this angular dipole deformation, we now have this kind of integrability picture, and even more excitingly, we find the same kind of Bethe equations and Bethe ansatz also for the spectrum of the appropriately deformed string theory side. So this correspondence for these examples really seem to survive this deformation process, which strengthens this conjecture for these models. Okay, thanks.
About the deformed Bethe equations, could you say a few words how they look like, how do they deform, does the spectrum change, and also can you write down the deformed R matrix here?
So, well, I mean, this work is, I mean, these spin chains, they have been known quite a while, and there's actually a paper by Bethe and Reuban who did this. And so there, in principle, it is exactly that spin chain.
Thanks for the talk. I was just wondering, so with Drinfeld twisted spin chain, a lot of, well, always, you should have a mapping between deformed picture and then undeformed with twisted boundary condition pictures. But here it seems that you're landing straight on the twisted spin chain. How does the deformed picture look like also from maybe from the gauge theory side? Because
that's a good question. So maybe to explain why this is reasonable for us. So, I mean, to land in this picture, the guiding principle is that we want to have gauge invariant quantities, and so it's natural for us to think in this star gauge symmetries, and it's just a natural it seems to be a natural consequence of that we end up in this twisted boundary picture. Anyway, there is something that is called a Seiberg-Witten map, which exists for these non-commutative field theories. And you can then express these star gauge symmetric fields, or star gauge fields, I would say. You can express them in terms of normal gauge theory fields in principle. And if you would, so the conjecture here, and like for these dipole deformations, you can actually show that if you use those fields instead to define different bases of operators, then this is where you find the twisted spin chain picture and not the boundary, twisted boundary picture.
So the twisted boundary conditions you have, do you fall under diagonal twists, or sometimes you find more general types of?
So, like, I mean, since we here started from a twist that is diagonalizable, like it's basically measuring charges of the fields. Well, it's really like just in principle in the spin chain language imposing phases. But the idea is, and this is also what we did work on, when you consider more involving twists, proper non-commutative twists, for example, you can also think on non-diagonalizable twists, kind of. But this is an open question whether these really then the field theory really follows the kind of expectation from spin chains.
Thanks. There's one question from Colio.
So in this formula, do you see double trace terms appearing naturally? I just don't remember.
So you mean in the action, or kind of like you're thinking of beta deformation where you also have the double trace interaction? Right, it's a good question. Like these things, in principle, we cannot exclude that we would need some corrections like this in the action to make the theory like have a proper scaling dimension. But the thing is, there's a paper already in the beta deformation that these things at the planar limit just play a role for very, very short operators. So as long as we consider something of length 3 or longer, we wouldn't expect those to appear. That's a good question. So in principle, this is something I'm also interested in and I would like to look at. It was just recent that we were even able to formulate these theories consistently. So it's an open question whether there exists an interesting limit and how to take this. It would definitely look relatively different from the normal fishnet limit, because it's harder to say that you have some interactions that are untouched by this. Like in the fishnet limit, for example, by taking this limit, you can strip off the gauge fields, for example. Something like this is, from my perspective, a little bit unlikely to happen in these deformations.
Okay, if there are no last questions, okay, let's thank Tim again. our last speaker is Elisabetta Armanini. She will tell us about scattering on the Coulomb branch of n equals 4 Suprian mills.
Hi everyone, thanks for giving me the opportunity to speak. It's a pleasure for me to talk about this ongoing work with Fernando Aldai, Kilian Herring and Sasha Ziboedov. So an interesting object that we would like to study and understand more is the gauge theory flux tube. And we know that thanks to the gauge and string duality, this is dual to an open string, which extends in the radial direction of AdS. So in order to probe the dynamics of these objects, we are going to consider the following observable. A 4-point amplitude of open strings that end on a probe D3 brane that is placed at some position Z different from 0 in AdS₃ cross S₃. This setup on the gauge theory side is dual to planar n equal 4 Superior mills on the Coulomb branch. This is just an X version of n equal 4 that can be obtained by giving a vacuum expectation value to the scalars, as Shota was explaining yesterday. So this is the amplitude, the object that we are going to study in this work, and let's see what are its properties. So if we consider the 't Hooft coupling to be small, we can compute the amplitude using perturbation theory. So for instance, at one loop is given by this box, where here in the frame we have some massive W bosons of mass m. So already at one loop, you can see that this amplitude has a 2-particle cut starting at 4m squared. But the most interesting property of this amplitude is that not only it has a 2-particle cut, but it also has a set of bound states. And these bound states appear as we increase g. And the reason is that the physical problem that we are studying is the one of the Coulomb potential. And indeed, as was studied in this work by Caron and Hen, we can actually match the bound states at weak coupling of this amplitude to the bound states of the non-relativistic hydrogen atom. Also at strong coupling, we have some control on the amplitude. So if we take the 't Hooft coupling to be large, and we take the soft limit, so small s and t, the leading contribution to the amplitude is given by the flat space 3-level scattering, and this is given by the very famous Veneziano amplitude. Then, of course, we can also have 1/g corrections, as we heard this morning. So these are going to probe the radius of AdS. And we managed to compute this correction here using the worldsheet bootstrap. The most interesting part, though, comes at finite g. So here we don't know anything about the amplitude. And what we would like to do in this work, so our goal is to combine 3 ingredients to be able to say something about the amplitude at finite coupling. In particular, we're going to use dual conformal invariance. This is an extra symmetry of this theory in the Coulomb branch. We are going to combine it with integrability and then with the symmetric bootstrap. So let's see how to combine these 3 ingredients all together. In order to do that, it's important to talk about Regge trajectories because these are an important topic to characterize the physics of the scattering amplitude. So let me remind you that, for instance, Regge trajectories in string theory have a very simple structure, so they are just straight, while, for instance, in other theories like large NQCD, they can also bend. In our case, Regge trajectories have a very peculiar form. So in particular, they bend, and they also diverge, and they diverge at s equal 4m squared. So this is the position of the ionization threshold, because for s bigger than 4m squared, we have a 2-particle cut, so we have the continuum. And the reason why these Regge trajectories diverge is because we have an AdS horizon. Then when s is large and negative, here the leading Regge trajectory goes like a log, as was studied in this paper. But the most important property of Regge trajectories in this theory is that thanks to dual conformal invariance, the computation of Regge trajectories can be mapped into the computation of a cusp anomalous dimension of a Maldassena-Wilson line in n equal 4 Superior mills with eventual operator insertion in the cusp. So this relationship is very precise, and it goes as follows. So the leading Regge trajectory is equal to the cusp anomalous dimension of a Maldassena-Wilson line with cusp angle phi, and the cusp angle and the Mandelstam S are related in a precise way. The subleading trajectory J1 is equal to a cusp anomalous dimension of a Maldassena-Wilson line with an operator insertion in the cusp. This operator is a scalar, and this is the same scalar that couples to the Wilson line. So this is why we call this phi parallel. So it's very interesting to see now how different limits of the Regge trajectory, in particular the leading one, can be captured by different physical quantities on the Wilson line side. So for instance, here the intercept is -1. Then when we turn on the cusp angle to be small, we see the Bremsstrahlung function B. When phi goes to pi, we have the quark-antiquark potential. while when S is large and negative, we have to analytically continue the cusp angle to be Lorentzian. When we send it to infinity, we see the light-like cusp. For the subleading trajectory, we have a similar structure, but it's a bit different because here we have a critical coupling, as was already studied in this paper. And below this critical coupling, the subleading trajectory does not diverge. So this means that below this critical coupling, we do not see any excited bound state. The punchline of this Regge trajectory discussion is the fact that these right-hand sides here can be computed using integrability of n equal 4 superior Mills, but in particular for any value of the coupling and of the cusp angle using quantum spectral curve, as was developed by Collier and a lot of people in this room. So now we have a way, thanks to dual conformal invariance and integrability, in particular quantum spectral curve, to compute the position of the bound states on the leading trajectory and on the subleading trajectory, and these will be useful inputs in the S-matrix bootstrap. So dual conformal invariance has also another important consequence regarding unitarity. So this dual conformal invariance, you have to think about it as an extra symmetry. And as you know, if we take, for instance, the case of the hydrogen atom in quantum mechanics, we have the usual SO3 symmetry. But if we combine it with the Runge-Lenz hidden symmetry, this enlarges the SO3 symmetry group to be SO4 on the bound states and SO1,3 on the scattering states. So our case is actually a relativistic generalization of this. So we have to take our SO3 symmetry and we combine it with dual conformal invariance. And this allows to expand the imaginary part of the amplitude. Instead of using SO3 partial waves, we are going to use these enlarged symmetry groups. So SO4 partial waves on the bound states when S is between 0 and 4m squared, and SO1,3 partial waves on the cut. So this is a new, let's say, enhanced version of unitarity. And this will be, as you will see in the bootstrap, stronger than the usual SO3 unitarity. So now the idea is to use the knowledge that we have coming from integrability of the spectrum of bound states and this enhanced unitarity to use them in the bootstrap to put some bounds on our amplitude. In particular, the usual observables that we bound into the S-matrix bootstrap are Wilson coefficients. So these are the EFT couplings that appear in the low energy expansion of the amplitude F. And let me point out that two of these coefficients are actually already fixed. So we have this 1 over ST given by the 3-level Glueballs exchange. And then we have A00, which is one loop exact thanks to a Norren normalization theorem from supersymmetry. So our target is to bound A10, A20, A21, or suitable ratios of them by using S-matrix bootstrap. And the way to do it is using dispersion relations. So the fact that we can write the scattering amplitude as an integral over its imaginary part. So we have an integral over the bound states. Here we are going to use SO4 partial waves and the knowledge of the spectrum coming from integrability. And then we have an integral over the cut where we are going to use SO1,3 unitarity. So let me show you some bootstrap bounds. So for instance, this is a bound on A10 divided by A00 as a function of the coupling G. So as you see in blue, this is the allowed region given by the bootstrap. And this is compared with a Bethe band that we generated using weak coupling expansion, strong coupling expansion data, and then some error model. So I want you to notice three important things. So first of all, this Bethe band is compatible with the bootstrap bounds, so it's inside the bounds. Then when G is equal to 0, you see that the lower bound is actually equivalent to the weak coupling data. And this can be seen better if we do this 2D plot, A10 versus A20. So we want to see what is the allowed region for this plot. Using SO3 unitarity, we find this region here encoded in this black line. But if we use SO1,3 unitarity, you magically see that the region shrinks, and there is a kink and a minimum, and this minimum precisely corresponds to n equal 4 superior Mills at one loop. So this was a surprising result because we saw that n equal 4 superior Mills at one loop on the Coulomb branch is extremal. Then here, notice that at strong coupling, the upper bound, our upper bootstrap bound, goes closer and closer to the strong coupling data. So, of course, these bounds can be actually improved. These are all preliminary plots, but we need some further inputs from integrability or, for instance, from localization. But I hope I convinced you that by combining dual conformal invariance, integrability, and this matrix bootstrap, we can derive some non-trivial bounds at finite G on this very interesting amplitude. Thanks.
decoupling. So
Yeah.
could you say more like how you computed that?
Yeah, so basically, so you have to, as Maria was saying this morning, so you make an ansatz using like a worksheet integral. And then you make this ansatz where you say this, you write your worksheet integral times a function, and this function has to contain harmonic polylogs up to some weight, in particular weight 3. And then we call it worksheet bootstrap because then you're going to use some inputs coming, let's say crossing, the usual things, but also we are going to use some inputs coming from integrability. So for instance,
Well, okay, wait, sorry. So just to clarify the question. So usually with that algorithm, on one side you have a worldsheet ansatz, and on the other side you have a CFT with a block expansion. But in this case, you don't have a CFT.
Exactly. Yes.
So I'm wondering what's the other side.
Exactly. Yeah. So we don't use the CFT because conformal symmetry is broken, as you said, and so we had really to start from scratch if you want. We make an ansatz. This is this worksheet integral. We have a function, and then we expand this function. And we have to fix the coefficients in this function using some inputs, for instance, coming from integrability. And this actually fixes the ansatz in a non-trivial way. I mean, we can discuss more, but Fernando input was very useful in this, and yeah.
There's one question from Julius.
You said more input from integrability would be useful. What exactly would?
Well, for instance, like the 3-point couplings. If there is a way to compute the 3-point couplings, so the residues on the bound states using integrability, this would be helpful to put in the bootstrap. But I think it's very hard.
On the spectrum side, do you need?
No, on the spectrum side, no, because we already have the leading trajectory, the subleading one, and then knowing the subleading is actually not so important for the numerics. So.
Does this relation with the cusp survive for example, excited states? You can have the cusp with operators inserted.
Yeah, so, well, we have a conjecture that this holds to be true also for subleading trajectories, but then you have to consider some operators that are these operators in 1D CFT, these L000 operators. But for now, we have we see that this works just when S is equal to 0, so when phi goes to 0. So it's actually non-trivial to generalize this for a general cusp. So, yeah, but it's a very interesting part to study and understand more how it works at subleading orders.
Thanks.
Perhaps my question is also a confusion that I have. I thought that when we were doing like this, this Coulomb branch amplitudes or something like that, we should see, at least for 4 points, we should see some sort of gamma octagon instead of some gamma cusp, right?
No, this is a different limit. Yeah, the octagon actually, if I'm not mistaken, appears if so these guys for me are massless and these are massive. The octagon, I think, is the opposite way around.
It's the other order, I see,
yeah.
I see.
There are other questions? If not, let's thank Elisabetta again and all the speakers of today.
Mike's